The next section, Chapter 8, concerns itself with rotational kinematics. Now, rotational kinematics, we mean, let's discuss the concept of position, velocity, acceleration, and so forth in a rotational environment rather than an environment where we have translation. Translation, as you recall, is motion along a straight line. Rotation is going to go around in a circle. So we're going to talk about what it means to have circular motion. And the circular motion is section 8.1. We certainly have a circle. It has a certain radius, r. And we're going to talk about a point on that circle as it's constrained to move on the circle. And the first thing that we can do is define what that angle is with respect to the x-axis. We could have a y-axis here, an x-axis here, but in particular we're interested in this angle, theta. This angle theta will tell us exactly where this particle is on this circle, just like x tells us where we are in a translational sense. So you might say that in translation, let's make a little table here. In translation, as opposed to rotation, translation we have x, and in rotation we have theta. These give us our positions. Well, how do we define this angle? We would say let's divide all of the circle up into 360 degrees. Well, that's somewhat an arbitrary result. And you'll notice that if we look at the length along this circle and call that length s, that this length s in relationship to the radius r are in a constant proportion for a given angle. If I went twice as far out here and looked at twice the radius, I would get twice the arc length s. Therefore, these are always for the same angle in the same ratio, and I can define a theta to be a dimensionless ratio s divided by r. In other words, it's how many of these, what a fraction is s of your radius. Now if I go all the way around the circle, then you know that that would be a theta of 1 revolution. And 1 revolution is 360 degrees. Well, what would it be in this case measuring with this new method of measuring the angle? The answer is, if I go all the way around, then s becomes the circumference. So I end up with the circumference, which is 2 pi r divided by r, and lo and behold, we find that in this new method of measuring angle, we have 2 pi as representing a whole revolution, or 360 degrees. This new measure is called a radian. And we will use radians whenever we are working with circular measurement, not degrees and not revolutions. It's easy to convert, so the first thing you have to do is to be able to convert from one thing to another. What, for example, is 1/4 of a revolution? 1/4 of a revolution would be up to here, because I go 1, 2, 3, 4. And that is, of course, 90 degrees. And if I do that, if I divide this by 4, I end up with pi over 2. So pi over 2 radians is the same thing as 90 degrees, or 1/4 of a revolution, or 1/4 of a period, if we're thinking of rotation. So now we have a new unit for rotation. That unit is measuring our angle theta, is in the new concept of the radian. Now, having that, obviously sometimes we have objects that turn. So we want to know what the angular velocity is, not the linear velocity. We could talk about the tangential velocity, the tangential, which we will do in a moment. But right now, what we want to do is define a new type of angular velocity. Angular velocity, omega. And omega is defined by the change in theta over a change in time. For those of you without calculus, it's the discrete change in theta over a change in time. If this is just the infinitesimal change, this would be how far did theta go in what length of time? So, for example, to work a problem, if I went halfway up here, 45 degrees, what would our radian be if I did that in 3 seconds? The answer is omega would be equal to my change in theta. What is it? Going halfway up. So all the way up to the top is a fourth of a revolution, or 90 degrees, is pi over 2. So half the way up would be pi over 4. So that's the same as 45 degrees. Now I'm going to do that in 3 seconds. So I divide by a time of 3 seconds. The answer would be pi divided by 12. Now since pi is 3.14159, you can think about it as 3. This is an angular velocity of about 3 over 12, or about 1/4. 1/4 what? Radians per second. And that's the unit that we use to measure angular velocity. Radians per second. Now that we have that, we can say, well, can the angular velocity speed up or slow down? Well, anyone who's ridden a bicycle know that, yes, you speed up or you slow down your wheels. They're going at one angular velocity, then now they're going to another one. So what can we do next? We want to define angular acceleration. The angular acceleration is symbolized by alpha, and it is the change in our angular velocity over a change in time, or using calculus for infinitesimal via d omega over dt. Again, if we take this wheel, which is turning at, what did we say the angular velocity was? Pi over 12, and we stop it in 2 seconds, what would our angular acceleration would be? Well, the change in omega would be from pi over 12 to 0. So we'd have pi over 12 minus 0. That's our change in omega. And I said we did that in 2 seconds. So alpha would be pi over 24. And that would be radians per second squared. So I've divided by another second here. And that tells us how to do angular acceleration. You can see also from this with calculus that while alpha is equal to d omega dt, omega is equal to d theta dt, so this is second derivative of theta with respect to time, or the second change. So what are the critical things here? Our definition of angular velocity, our definition of theta, measured in radians, and our definition of angular acceleration. And so now we have something comparable to our translational case. We have position, velocity, and acceleration, but they're angular, meaning they are all measured in radians, radians per second, or radians per second squared. If we were to take one final example, we could say, let's suppose that something makes a revolution. Let's say it has 13 RPMs. Let's say 10 RPMs. What do we mean by RPMs? We mean revolutions per minute. You can also have RPS, or revolutions per second, or revolutions per hour for things going slowly. So how would we convert this? We know that that's an angular velocity, omega. How would we convert it to our standard form? Well, omega is going to be equal to 10 revolutions for each minute. So what's a revolution? It's going to be 10 times a revolution is how many pi? It's 2 pi. That's one revolution. And we've got to divide that by a minute. How long is a minute? 60 seconds. And this is a radian. 2 pi radians in one full circle. We're going at 10 full circles per minute. So what is this going to be? This is going to be 20 pi, so it's 20 over 60 times pi radians per second. And that will give us our angular velocity. And so it's going to be about pi over 3. Well, that's another second example of how we would compute that. And next, what we're going to do is relate this rotational motion to translational motion.